All right. Okay, let's start. Okay, welcome back. Today is the November 4th, 2024. And we are now on week 12, Monday's lecture for EigenValues and EigenVectors. We'll finish the EigenValues and EigenVectors chapter. Specifically, we'll go through 8.1.3 until maybe 8.1.5. And let's see how far we can go. But today, again, as usual, we are doing it at a different speed. So if you want the real details, you have to watch the YouTube videos. And after that, we are finished with all our lectures for our CA as well as exam. And in week 12 on Friday, we are going to do some revision for the CA and the part 2, my part. And then on week 13, you have to do self-study if you want to for SVD. And I would drop the folder into the NTU Learn, but this is not included in the exam. Okay, so I guess most of you guys will ignore it, and then we'll stop at week 12 for all your study materials. With that, let's begin and see what we're going to do. All right, let's revise what is eigenvalue first and eigenvector. So the basic idea is A is square. And when we have a square matrix and we can multiply with a vector x and we get an expression like this, then what we realize is that the vector x1 being eaten up by A, transformational, is changed only by a scalar value. So you can think of it this way. This is the transformation. This is x1 going in, and then out comes lambda x1. And then you say, what's so special about it? And this is very special because typically when you throw a vector into a transformation, A times X is the transformation of X, then the direction of X changes. Okay? So if this behavior exists, this is a very special kind of change. And I'll give you an example. Let us have 1, 2, for example, x1. And if lambda 1 is equals to minus 2, then basically it is minus 2, 1, 2. So it becomes minus 2 and 4. Minus 2, minus 4. So please be careful, all right? The direction is the same. Then you say, where in the world is the direction the same? Well, if you sketch this, where is 1, 2? 1, 2 is here. Where is minus 2, minus 4? Minus 2 is here. So the blue is the input vector called x1. And here, the green is the output vector y is equals to ax1 is equals to minus 2 times 1, 2. And when we say that the transformation maintains a direction, opposite direction, yeah, negative of the direction is still the same direction in our idea. Okay. Now, if 1, 2 is an eigenvector, what is, guess, 0.5, 1. So now we call x1 an eigenvector. What about this guy? Can someone write? Can someone tell me, please? If x1 is an eigenvector, is 0.5 and 1. So now let's now draw 0.5 and 1. 0.5 and 1 is here. This is 0.5 and 1. And then when we submit this through A, and output is 2 times this vector, which is 1, 2. Sorry, minus, the eigenvalue is minus 2. Minus 2 will be multiplied by this vector. It will be minus 1, minus 2. And it will be this vector. Maybe I should draw in red. So again, the orange is transformed into the red. So you'll realize that the word eigenvector, it is any vector, any vector in the direction of 1, 2. And later MATLAB, you realize is that you normalize 1, 2 into a, a normalized vector. Basically, 1, 2 will be divided by the norm of this vector. Okay, so this is the first thing that you must remember. Okay, for the quiz, yeah, definitely. All right, let's try second one. Now, the second problem we are faced with is this. We know that A, and if x1 is an eigenvector, out comes the eigenvalue and x1. And if x2 is also an eigenvector, lambda 2 times x2. Oh, I have to turn off your microphone. How do I turn off? Mute all. Okay. All right. Now, so when we write this way, we are saying that x1, x2 are eigenvectors of A. But when we talk about eigenvector, we must tell you the corresponding eigenvalue. So when we do A multiplied by x1, it will be scaled by lambda 1. When we do A multiplied by x2, it will be scaled by lambda 2. And lambda 1 and lambda 2 can be real, can be complex. Okay, later on you'll realize. Okay. But maybe for simplicity, we'll just try everything real. We'll just show you some complex eigenvectors and values later on. Now, the other way to generalize this is that we don't like to write it in so many forms. We like to write it in matrix notation. So I'll give you an example. If A multiplied by x1, then we realize that we told you that it will be lambda 1 times x1. But this is exactly the same as x1 times lambda 1. Okay, no difference, huh? Moving the lambda in front or backwards. Of course, like before, in the last lecture, I also did this. And now, of course, this is more exciting. Since A, for example, let's just do a simple one, 2 by 2. And therefore, this guy is also a 2 by 2. And now, we're going to put x1 here and x2 here. And now, if you observe carefully, right, A times x1 must be x1 times lambda 1. So lambda 1 is here. So lambda 1 is going to scale this column. Do I need to do anything with the second column? No. So I put 0. So I repeat. A times x1 should produce lambda 1 x1. Now if I have a matrix lambda x1 and x2 here, I'm going to generate, later on you will realize that I'm trying to generate lambda 1 x1 for my first column, lambda 2 x2 for my second column. But how do I get this? Is simply lambda 1 and 0 multiplying by these two columns. Lambda 1 will multiply by this column to get lambda 1 x1. The second column is not used, so I put a 0 there. Let's see the second guy. The second guy, I need it to be lambda 2 x2. I have already x2. So I need lambda 2. Where do I put the lambda 2? Since this is in the second column, lambda 2 is here. Now, what is the value on top? Is 0 because basically I want 0 multiplied by the first column, lambda 2 multiplied by the second column. So you see, it is this way. And therefore, this becomes here. So then you look and you say that this is more complicated than it is. No. Let us call this matrix P. P for eigenvectors. I don't know why. Is A times P, right? A times P is equals to, here is what? P again, right? This is still the eigenvector P. And D, what is D? D is the eigenvalue at the diagonal. So the 0 is the notation for diagonal. So diagonal. So what is P? P are the columns of eigenvectors. And then please remember that the columns must be corresponding to the corresponding eigenvalue. Because remember, x1 is associated with lambda 1, x2 is associated with lambda 2. So the columns are important. If you switch this wrongly, then all the numbers are wrong. Now, lastly, if P is full rank, then P minus 1 exists. First and foremost, A must be square. P will definitely be square. And if P is full rank, then P minus 1 exists. A, P times P minus 1 multiply on the right hand side equals to PD P minus 1. Here becomes what they call it, identity. A is PD P minus 1. This is called a diagonalization. Why diagonalization? Because matrix A has been changed to matrix D. What is P and P inverse doing? We'll show you later. All right. And in fact, this diagonalization belongs to something called similarity transform. All right. Okay, so we are done here. So let me show you the slides for similarity transform. Here. In 8.1.3, if I can find a matrix P such that A can change into PB minus 1. Whatever P is, whatever B is, then B and A are related. In our example, A is being changed into PDP minus 1. So we're talking about A and D here. Here, they are talking about B. Any matrix, it doesn't need to be diagonal. Okay, it doesn't need to be diagonal. But we always want to transform something to a diagonal matrix. If it's not diagonal, it's not very exciting because it doesn't have the properties of the diagonal matrix. And maybe this is the key insight here below. Similar matrix represents the same linear map, same linear transformation A under different bases. All right. And what other things that similar matrix can give us? This is all the properties that A and B or A and D have. So the determinant of A is the same as determinant of this whole matrix. Let's call him B. Okay, that's the idea. All right. Now, let's continue. So I would do this one more time. 1A. Now, I give you a matrix, and in our quiz, at least, we'll always play with 2 by 2 matrix the most, unless we give you very special matrices. Otherwise, it's impossible to be able to answer it quickly. All right. So I now give you A. And of course, then, I'm going to ask you now to use MATLAB just so that you can get your answer faster. And then you can say ED equals to EIGA. So this command basically says perform eigenvalue decomposition and drop the eigenvectors here as columns and drop the corresponding eigenvalues here. All right, I'm going to show it to you now. What is it? So I written my A, which is minus 3, 12, minus 2, 7. Okay, I can't expand this, so you got to squint your eye a bit. And now I'm going to say ED. Basically, the output is 2 matrices. The function I call is EIG, and out comes E. Then the nice thing about the eigenvalue is here is very nice. D is equals to 1 and 3. So the eigenvalue is 1 and 3. Let's call him lambda 1 and lambda 2. What about E? The corresponding E is a hopeless value, minus 0.948. And here is minus 0.316. This guy, let's call him x1 for eigenvector 1, corresponding to lambda 1. The other guy, minus 8.944, 0.8944, and the number is minus 0.4472. Now, guys, this number doesn't make sense. But if I write it in another form, remember, the vectors are normalized. It is pointing to a direction with norm 1. What about these numbers, guys? How are they related? Please answer the question. They are in the same direction opposite to this guy, right? Minus 0.948, minus 0.316. This is ratio of 3 to 1, same 3 to 1. Minus 0.8944, minus 0.44, 2 to 1. So let's call him E1 and let's call him E2. A is equals to what? E1, let's finish this equation. E1, what? This? E1, I'm going to write what here? E1 times, anybody? E times E1 minus 1. Now, what about E? If I use E2, What do you think I will write here, guys? Anybody? E2? Are you all still here, guys? Yes? Yes, great. E2, D, E2 inverse. So the two ways to write A is here. Again, I'm telling you, only the eigenvalues are unchanged. The eigenvectors will be changing all the time. Okay? So in the quiz, yeah, you know, don't be mistaken about the eigenvectors I'm giving you. All right? So let me try. E times D times E inverse is same as A. Yes, minus 3, 12, minus 2, 7. Now I change my E to become E2. My E2 is, what's my E2? 3, 2, 1, 1. Then compare E and E2. Totally different, right? But actually, they are the same eigenvectors. So E2 times D times inverse of E2. Answer is same as A. Voila. Again, okay, this is to drill into our head that eigenvectors are nothing but directional vectors. Okay? All right. Now let's continue with this. So this is the slide. Next slide. Let's try 3. Are all A diagonalizable? What do I mean? Marvin asked me, what do I mean? The eigenvalues of A is 1 and 3. The eigenvectors, I can represent it in E1 or E2. Do they look the same? They don't look the same. But actually, they are the same. They are pointing to the same direction. Marvin, is that okay? Okay, thanks. So now the question is, are all A diagonalizable? So I'm going to give you A equals to 1, 0, 1, 1. This is very innocent, right? It looks very, very innocent. Yeah. First is it invertible, guys? Is A invertible? Yes, correct. There is one pivot here and there's one pivot here. A is definitely invertible. Does A, does A, or it does A have is, or I should say not does, is A diagonalizable? Answer. So then you say, okay, let's try E D equals to EIGA. Of course, in the exams, you don't have your MATLAB, but let's try. Okay, let's put A first, guys. A equals to 1, 1, 0, 1. Can you all see? What did I, what did he give me for E? So E becomes 1, 0, minus 1, 0. D becomes 1, 0, 0, 1. So, so what is lambda 1, guys? Lambda 1 is 1. What is lambda 2? Same, 1. So the roots of the characteristic equations is repeated. The same eigenvalue. The, what is that called? The algebraic multiplicity of this eigenvalue equals to 2. The eigenvalue 1 is repeated twice. Algebraic multiplicity is 2. Now, we are again hoping For each eigenvalue, can we find the corresponding eigenvector? He pops out this for the blue one. I should draw the correct color. And then for the green guy, he pops out this. Any problem, guys? Any problem with this E? Yes, what's the problem? E is not what? Invertible. The columns of E are dependent. There is only one eigenvector for lambda equals to 1. There's not two. So we do not have enough. Not enough what? Not enough eigenvector to form a basis. Therefore what? What's the word I'm going to ask to say? Not what? Diagonalizable. So that's a very strange thing, right? A looks very, very innocent. A is invertible. But yet, here, this is not diagonalizable. The more details here. Here are the details of what I'm. When is A diagonalizable? You can read about this. Okay? All right. So therefore, now everyone is very interested in when is A diagonalizable? When is A diagonalizable? One, if A's eigenvalue are distinct, then each eigenvalue have corresponding eigenvector independent of other eigenvector, implying distinct eigenvalue will means A is diagonalizable. Okay, I don't prove. The proof is in the lecture notes. So every time you see that if you ever have the characteristic equation and all the eigenvalues are distinct, means there's no repeated, then this matrix is diagonalizable. So now I give you an example. A is equals to 500 minus 800, 17 minus 2. Is A invertible? First question. Second question. Is A diagonalizable? So in the quiz, what will happen is this. True, false statement. Maybe the question is, I give you a matrix and I say A is invertible. A is invertible. Then I ask you to put true or false. Then our A is diagonalizable. True or false. And then the quiz is this, guys. For example, only, this is statement 1, statement 2, small little a, Only one is true. Only two is true. C. Both 1 and 2 are true. D. Both 1 and 2 are false. Choose. This is a type of quiz question we'll have. For example, do you need me to repeat, guys? Anybody? So let's try. I give you a matrix like this, and I say A is invertible. A is diagonalizable. Then I ask you to determine the status of this, right? So let's determine whether A is invertible or not. Is A invertible, guys? Can we do it together? False. Very good. False. Why false, guys? Because there is only 2 pivots. Second question, is A diagonalizable? A diagonalizable? I just did this, right? Distinct eigenvalue, right? So phi 0 minus 2. A is diagonal, true. So only 1 is true. Only 2 is true. So this is the correct answer. Right? Yeah. So this is the type of questions that you will face in the quiz. So it's non-trivial because, my goodness, you have to get everything right, and then the selections is multiples of these questions, right? So it means that there's no chance to guess. Right? Okay. So, all right. In this year, at least, in this year, we are not going to do okay, practice. Complex eigenvalue and eigenvectors. Okay. So A is real. 1, 1 minus 1, 1. So what do you think A is, guys? If A is a matrix that will act on X, A, X, what? And if this is the input blue, let's call him E1 and E2. A acting on E1 will move to where, guys? A acting on E1, which is what? What's E1? 1, 0. Will basically pops out 1, 1. Where's 1, 1? Let's put the green. So E1 will become this one. Let's call this Y1, for example. What about E2? A acting on E2 will pop out minus 1, 1. So minus 1, 1. So this matrix rotates E1 and E2 by 45 degrees anti-clockwise. So in this case, then you'll be looking at this matrix and say, there is nothing. All the vectors will move. No vectors will remain in the same position, right? Guys, can you all follow me? It is now obvious to you that A acting on E1 will move to Y1. A acting on E2 will move to Y2. No vectors in this plane will stay still except the 0 vector. The question now is does A have eigenvalue and eigenvectors? Because it doesn't make sense, right? It's going to move. Everything is going to move. how to have eigenvalues and eigenvectors. Right. So again, MATLAB is our calculator, and let's just dump it in and let's see what he does for us. A equals to 1 minus 1. 1, 1. 1 minus 1, 1, 1 for second row. ED. Voila. Outcomes. E is equals to 0.707 plus J0. Complex value. 0 minus J 0.707. That's the first column. This is x1, the first eigenvector. Second one, 0.707 plus 0, 0.707, sorry, 0 plus j, 0.707. This is x2. So you see, oh, MATLAB can tell us we can live in the world of complex numbers for eigen decomposition. And D is equals to, what's the value? 1 plus j, and the other value, 1 minus j. Now, and then to make sure that we are doing it correctly, E, D, E inverse. And then let's try. Okay. E times D times inverse of E. I get back 1 minus 1, 1, 1. Okay. So this is no problem. I can get back the same A. Okay. So it's very interesting. In the real world, in this rotation matrix A, there is you can't think of any eigenvectors and eigenvalue. But if you omit the use of complex numbers, then you can see that eigenvectors and eigenvalue exist. And you can in fact find the inverse of E, a complex inverse matrix. All right. So as for eigen complex numbers, okay, and then we are now off to the powers of A. So I think I've done this the last time, but let's do it again. Now, if A is diagonalizable, it means that A equals to PD P inverse exists. Exists? Who exists? P inverse exists. Why P inverse exists? Because we have sufficient number of eigen vector spanning Rn, n by n. Just now in the other example, we show that, hey, we have eigenvectors, but they are not enough. Yeah. So P inverse don't exist. And the reason it don't exist is because we have repeated roots, and these repeated roots didn't produce enough eigenvectors. So maybe quiz question number 1. If distinct eigenvalue implies diagonalizable, true or false? True or false, guys? True or false? True, correct, true. Repeated eigenvalues imply not diagonalizable. True or false? Yes, it's false. Sometimes true, sometimes false. Not always true, not always false. So false. So it's yeah. So these are the type of quiz question you will have. All right. Now, but let's now have the nice case. A is equals to PD P inverse. A squared PD P inverse PD P inverse. We can open up the bracket. PD D P inverse. And remember that D is diagonal. So let's call him lambda 1, lambda 2. So this is D and D. Answer is, guys, this is very easy. Diagonal matrix multiplying by each other is trivial because actually you think of it this way. It is this guy times this guy to get the first element. Lambda 1 times lambda 1 is lambda 1 squared. 0 times 0 is 0. So, okay. How about this guy? 0 times lambda 2 times lambda 1. So 0 times lambda 1 is 0. Lambda 2 times 0 is 0. About the blue and the orange now. Lambda 1, 0 times 0. Lambda 1 times 0. 0 times lambda 2. So 0. And the last guy is the green. 0 lambda 2, 0 lambda 2. Answer is lambda 2 squared. So therefore, d square is nothing but what? D square is very easy to calculate. P d squared P inverse. And then in fact you can do AK, where K is any integer, positive. Huh? So it's P d K P inverse. So this is the powers of A. All right. Now, let's try something. What do you think A 100x looks like? Guys, anybody? You've seen, I mean, I show you what is AX look like. AX looks like P D P inverse X, right? Yeah, so it's P D 100 P inverse X. Agree? Yes. No, you forgot the X, guys. A 100X. You have to have the X there, right? Just like AX equals to PDP inverse because this whole thing is A, right? So AX equals to PDP inverse X. So A to the power of 100X is PD 100 P inverse X. So now the question is, what in the world is this guy doing? So let's revise. Change of basis. Okay? So you'll realize that P inverse X is a change of basis. All right, let's see. Now, do you remember this? X in the standard coordinate, we represent it as a vector. And here is a vector of, let's say, Rn. Correct? And we don't even write the word standard. If we don't write the word standard and we just put it like this without any subscript, then we are in the standard basis. What is the standard basis, guys? What is the standard basis? Can someone tell me for R2? Is this one? 1, 0, 0, 1. So this is E1, this is E2. So therefore, if I say I have a vector 2, 3 in the standard basis, what am I actually telling you, guys? Remember, right? These are just representation of a coordinate with respect to a basis. But what am I telling you? 2 is acting on E1. 3 is acting on E2. How? This is actually 2. This guy is with respect to the first basis. This guy is scaling the second basis. 2 is scaling the first basis. So every time when I'm giving you a coordinate system, 2, 3, you should be thinking this, okay? Please don't think of it as 2, 3 in that point, in that space. You should be thinking 2 times the first basis, 3 times the second basis. Clear? So once you understand, oh, a coordinate vector has to act on, it acts, yeah, on the basis. Now I'm going to give you another basis called B. And B has another basis. Oops. Oh, let me give you a basis. B is 1, 1, 0, 1. Anything wrong with this basis, guys? B? First, my question to you is, does B spans R2? True or false? B spans R2. True or false? B's basis spans R2. True or false? True. Because these bases, even though they are not orthogonal, they are not dependent. Using these two, I can reach any point in R2. So true. This is a basis that spans R2. I want to represent 2, 3 using B's basis. So what is B? Yeah, what is B? 2, 3 is my point in the standard basis. How do what am I going to equal to? 2, 3, right? This is a standard basis. What am I going to write here, guys? Something times B equals to this. Same, right, guys? On top. What do you think I'm writing here? Okay, I better erase so that you can see what am I trying to tell you. 2, 3 is actually what? 1, 0, 0, 1 multiplied by 2, 3. I'm using the standard basis here. I'm using the x in the standard basis to give you the number that I'm expecting. And then you say this is nonsense because this is identity, right? It must be the same. But now, now if I do not Now I'm saying, let's go and get 2, 3, but using the B basis. So now I'm asking you to do this. Put the basis here. And now what is the value that I should put here to reach 2, 3? What am I talking about, guys? Okay, let me draw you a picture. The weights. Yes, the weights acting on the basis. Let's call him B1 and B2. All right. I'm going to draw you a picture now. One, 1, 2, 3, 4. 1, 2, 3, 4. 2. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to go to 2 and 3. Where's 2 and 3? 2, 3. Yeah, right? Should be here now. Oh, it's so bad. 1, 2, 3. This is the vector 2, 3 in the standard basis because I'm counting 2 here and I'm counting 3 here. But I want to use the B basis. The B basis are 1, 1 and 0, 1. So I'm now going to draw you 1, 1. 1, 1 is here. 0, 1 is here. I'm going to use the blue and the green to reach this point. How do I travel, guys? Anyone? How can I use the blue and the green to reach this point 2, 3? 1, 1. Then the next time I move is what? If I move the blue by another bound, becomes what, guys? If I move the blue by one bound, becomes 2, 2, right? So this is equals to 2 times 1, 1. 2 times the first guy. Now I want to move up, right, by the green. So this is 1 times 0, 1. So therefore, I can reach 2, 3, the standard coordinate, using the B basis by the weights 2 and 1. So this guy, the x vector, this is the x vector in the standard basis. This is the x vector in the B basis. I'm using this to weight the basis vectors to reach the same point in the standard basis. So this is the change of coordinate. This guy is the standard coordinate. This guy is the coordinate in the B basis. Everybody clear? Oh, I'm running out of time. But we're almost done. How's that? Clear. All right. Now the magic, guys. X in the standard basis is called B, the basis, times X in the B basis. Everybody's happy with that. Is the B basis square? Yes. Is the B basis invertible? Yes. Therefore, B minus 1 exists. Agree, guys? And therefore, now I'm going to pre-multiply on my left. And therefore, now X is B. Clear? Now, what happened, guys? Something very exciting happened. I have changed my X and I figure out how to change it into the coordinate of the B basis. I mean, here was like, Wow, one hell of a pain, right? Trying to figure out what are the weights by graphical. But now it's trivial. This guy is simply, XP is simply this guy inverse times X. Finish. Now, let's take this picture. X is in the standard basis, multiplying by B. X is in the standard basis. Multiplying by P inverse. So what happened to this blue guy? What do you think is this blue guy? He has a name. He is X in the P basis. Get it? So he is X P. Okay, everybody? Happy? All right. Now you realize uh, that by doing this step, by changing X from the standard basis into the P basis, D, which was actually A in the P basis. Right? That's where the first sentence is. But if you have problems understanding all this, I'll show you where we were. It is in 8.1.5b or 8.1.5b, eigenvalue, eigenvectors. And I'm explaining the last part of this diagram, this nice diagram over here. Okay, X, P inverse changes X into the B basis. Okay, let's do this diagram together, guys. Abstractly, I say my input X can be transformed by linear transformation T. Y equals to Tx. T operates on X, spits out Y. Finish. Linear transformation. Nothing to do with matrices. I then change my X, the abstract vector X, into Rn space, a vector of elements, and I cast it as the standard basis. A is the representation of the transformation as a transformation matrix. A operating on X is the equivalent of T operating on X. So this is easy to understand. This is this is PDP inverse X is still okay. We realize that A can be changed into PDP inverse. No problem. This is non-trivial to understand. Okay, let's try. But we also found out that that our equation right here, A100X basically is P inverse times X standard. X P inverse operating on X. And we also realize that this changes P inverse X is nothing but X in the B basis. Okay, fine. We have changed X into a different basis. We operate X on D. We're only doing AX, okay? A times X. So D is eating up X. So YB, the output of this is Y in still the B basis. But we're not happy with the B basis. We want it to get back to P basis. So how? Look, the P is sitting here waiting to eat up this output to transform the operation back into the standard basis. What am I talking about, guys? Here. If my input is xb and I multiply with b, I am transforming xb into the standard coordinate. If I'm in the standard coordinate and I'm pre-multiplying on the left by b minus 1, I'm changing it into the xb. So this is the confusing part to many students. As long as you get this straight, then this is easy to interpret. So these figures now become clear. This is abstractly showing you what's happening. Why are we playing with all these matrices, transforming them? Because A times X is difficult, but D times X in the B basis is trivial. This is the reason why we are playing with eigen decomposition. One of the reasons. Okay, and I think with that, I'm really quite done. Let me see.